Is that a good compromise lighting? Nice thumbs up, thumbs down. Turn the front ones off. All right.
Is this big enough for everyone? I'm not sure if I can do anything about it, but.
There's one.
I'm going to drop it down here because the glare from that back.
You can keep coming.
Ray, can you see the bottom of that screen still on the back?
You can come. You can come all the way down if you want.
That is all the way down.
Okay.
Okay. So welcome everyone. Thank you for coming. This is being videoed so that it can be actually put up on a website. And we've had requests to view this seminar from a lot of the resident directors, their research staff all over the state, as well as other people. So we'll make this seminar available through whatever you call it when you put video on the internet. So today's seminar is our first candidate for our Chief Water Scientist position for the Texas Water Resources Institute, Vince Tidwell. Dr. Tidwell is currently a distinguished technical scientist at Sandia National Laboratories, where he has worked for the past 23 years, focusing most recently on energy-water nexus, and has a breadth of experience in collaborative modeling and team building. He has his PhD from New Mexico Institute of Mining
and New Mexico Tech.
New Mexico Tech. Just live right there. So at any rate, anything that needs to be filled in the blanks, I'll let Dr. Tidwell do that. But thank you for coming, and welcome, Vince.
Thank you. Do I need to turn anything on in this, or is it on? Okay, very good. Thank you. Appreciate all of y'all spending a little bit of your almost holiday weekend with me. What I'm going to do today is I'm going to take a pretty high-level view of a lot of what I've been working on for roughly the last 12 years instead of taking a deep dive in anything in particular. But hopefully, by doing this, you'll get an idea of really what I've been working on and kind of helping to evolve over these last 12 years. And they all work around this theme of collaborative and integrative modeling, multidisciplinary modeling to address issues around water, energy, and other natural resources and their planning. And I do want to say I've really been blessed working with a really great group of folks at Sandia over the years and from a number of other institutions. And I just want to say that everything I'll be showing, I've been helped by a really great group of folks. So where are we going with this? I think overall, throughout the U.S., throughout the world, this issue of sustainable water development and natural resource development is a major issue. But I think after coming out of this major drought, Texas, has probably a very unique and more honed idea about sustainable water development. It's more on the forefront of people's ideas and concerns. And as we go forward, kind of looking now from outside, hopefully, of this pretty significant or really once in a historical time period drought, is how do we begin planning for sustainable development going forward? And what are the challenges that we face? And certainly we're all aware that Texas and really many places in the U.S. is growing very rapidly. But that growth in terms of water use is very important, but there's also this coupling, and there's also this growth in demand for electricity. That growth in electricity demand also has an impact on demand for water. Depending on what we do with agriculture, changes in land use, that affects energy, it affects water. So all of these demands for these natural resources are tightly linked and very complicatedly linked. And what we do in one is going to affect the other. The other thing that's a challenge is environmental health and properly evaluating that and integrating it into our analysis and understanding how we can protect that environment and to what level to protect the environment along with all these growing demands and how we meet those. Also, we're faced with the variability of climate and the specter of climate change and what impacts that will have. And so some uncertainties, large uncertainties going forward. And then if all these physical issues, all these physical processes are not challenging enough, then to overlay all the human dimension of this, the disparate values that we place on water and other natural resources, just the different ways we interact with these resources, again, all make this a very challenging but very interesting problem. And so I think if we are to achieve some level of sustainability in our development, we're not going to be able to do that by just intuition alone. We need some tools to help us to look into the future, to understand how these complex systems interact with each other, how we address these differing values, the uncertainty and whatnot. So we need tools that help provide a informed basis for decision making. But it's not enough just to have the best models and tools in the world unless we can really convey the information to the public and to do it in a transparent way, in a way that they're comfortable and we've missed the boat. So we need tools, processes to be able to engage the public. Not just at the end of the day, we don't just create a tool and then throw it over the fence and say, go and make your decision. No, I think there needs to be a much tighter implementation of the engagement of folks and the tools that we develop and use. And that's basically, with this idea in mind, is really what I've been working on in some way or another for roughly the last 12 years, and that's collaborative modeling and trying to develop this as an approach. And basically the idea is very simple. It's really, instead of waiting until you've developed a tool and then encouraging folks to interact with you and do some kind of decision analysis, the idea is engage them right from the beginning. Get them involved. Help them or use them to help define what is the causal model, to understand what are the important causal relationships, what's the important issues that we need to be addressing. Then going forward and understanding this kind of information, then quantifying it. What data should we be using? Who should we be interacting with? So, of course, that adds a little bit of effort into the overall modeling process, but hopefully at the end of the day, we've gained some important things. A, we've connected with the stakeholders. They have experience and knowledge that you're just not going to get any other way. The other thing is more transparency in the process that hopefully down the road will lead to more consensus in the results, a better understanding of the black box. The model is not a black box as much anymore. And also, it's structuring the group, the thinking, the discussion, and stimulating group learning. And a lot of times the model almost becomes secondary to this learning process. And by the time you get to the end of the process, you've pretty much worked things out. So now I want to give a few examples of some work. And like I say, at a very high level, I'm happy to share any of these in more detail with you later on. But I'm choosing a whole set of examples basically for the Middle Rio Grande Basin, very near where I live. And the reason I chose that is because you can see a real sense of how this idea has evolved over time. And I mean, it's almost kind of like if you start with a little onion, and now I'm going to kind of be adding layers to it as we move out in terms of how this idea has grown and evolved over the years. And so we started back with this idea about 2001. And our first implementation of it was with this state water planning process, very similar to what y'all do here in Texas. State engineer broke the basins up, or the state up, into 13 regions that make no hydrologic sense, but we worked with the Middle Rio Grande region, which was a 3-county region in which Albuquerque, the largest city in New Mexico, sits, and where I'm located. And basically the problem was pretty simple. We need to understand what our future supply is, how much water do we need now, and how is that going to be changing into the future, and then we got to balance that over the next 50 years. And so that was basically the idea behind what we needed to do. And so we wanted to implement this collaborative modeling idea. So what we did is assembled a cooperative modeling team, and that included representatives from this grassroots planning group that was supporting the state engineer for the Middle Rio Grande region. And basically we had people that represented farming interest, environmental interest, urban development interest, basic technical folks as well. And we also included the decision makers, the Middle Rio Grande Council of Government. They're the guys who'd have to apply this in some sense down the road. And then we had some professional facilitation through the Utton Transboundary Resource Center at University of New Mexico. Basically, the way this worked is we met roughly every other week with this group of folks for an hour or two, and we built from the ground up this model together. So we'd come in, what's the issues that we need to be addressing? How do you go about making decisions about how to use water if you're a farmer? And we'd use this kind of information to conceptualize the models, and then they'd help guide us to data, et cetera, and then they would review the model as we put pieces together. And then we had all kinds of other engagement with the broader community from there. And so just as a point of reference to give you an idea of what all this looks like, this is the oldest thing, the very first model we put together like this, but an important part of this is we wanted to create a tool then that here on my laptop we can carry right back out to the community and work with them to help in some of the decision making. And so although this is the oldest and probably the simplest model, it conveys the ideas that I'm trying to get across pretty easily. So again, the idea was to be able to look here at this Middle Rio Grande region and to understand where the issues are to begin with. And so you can sit here and run the model, and this is just kind of the dashboard, the very front end of it. And what they were most concerned about is the Rio Grande Compact. This is basically a measure of the water balance of the surface water system. So it's measuring the amount of water we have to send downstream basically to Texas and very southern New Mexico. And what this shows is historically we were running a deficit coming out of the 50s, which we all remember the strong drought. Then some of the wettest period on record here is through the 80s and 90s. And then going forward, the projection, and this is an average, we can run this stochastically many times, but the idea here is that on average, we're expecting to see some problems in meeting that compact delivery because of many reasons, the city and some of the things that they're employing, the fact that this has been an unusually wet part of the history and whatnot. So this suggests that we're going to have some problems meeting our compact balance. In fact, we couldn't run this kind of deficit. The state would sue us. You guys would sue us anyway. So the other has to do with the groundwater balance as well, okay? And so we know there in the Albuquerque region we're depleting the groundwater. And in fact, you see this little point of diversion there. And what that is the city beginning their San Juan Chama project. They're actually taking water that's being diverted out of the Colorado River and using it for drinking because we've been depleting the aquifer. We got groundwater subsidence or depletion. We got ground subsidence associated with that, higher costs, a lot of problems. So we know we need to do something. City's beginning to take some steps, but if we don't cut back water use and growing population, we know we have a problem. So the idea is the model gives us an idea of communicating what some of the issues are. But now the question is, where do we go from there? What can we do about this problem? And so we also went to the, let me see here. We went back to the public, and so in working with this, they came up with a whole list of different options that they would like to see or that they would be open to seeing used to help balance this water budget. So things that had to do with the agricultural sector, the bosque, which is the riparian area along the river, residential, non-residential, desal, reservoir, reoperations of a few things. And so just to give you an example of how this would work, we know we have some problems. Well, what if we were to go in and encourage the population to implement low-flow appliances in their homes and require all new homes to use low-flow appliances? And we could do this both with residential and non-residential sectors. And so what would that one simple change do to our system? And so see the blue here, and so you can see how quickly the model ran. So we can sit here in a kind of a stakeholder process and do this. We can see what it cost us. We can see what the impact was on the groundwater depletions, and you can see that, as you'd expect, because we're using less water in our homes, that we're depleting less groundwater. But what we end up seeing is an impact on our ability to meet our compact delivery. Now we're in worse case than we were before, than we started off. Most of you probably realize what's going on here, but we've also set this up where you can dig a little deeper, go down and see what's going on. And basically, as you might expect, what's happening is we've been pumping groundwater for all of these years. We're not consuming that water in our homes. We're we're sending it to the wastewater treatment plant, treating it, and then releasing it to the Rio Grande. And so when we start conserving water, we have less wastewater discharges. So that reduces, but this is a lot bigger change, delta, than we were seeing with the river. So there's actually something else going on, and that's the interaction with river leakage. The fact is that when we pump less, we're going to have less leakage, which leaves a little bit more water in the river. And so the overall, the balance between the two is a net loss, like we were seeing here, of, you know, a few tens of thousand acre feet per year. So kind of a non-intuitive idea unless you really kind of knew what was going on in the basin. So these tools help us to see things that we may not be able to see otherwise. But the other thing that we can see very clearly is this is not going to get it for us, right? We haven't balanced our groundwater budget, and we're doing worse in our compact. So we're going to have to put more than one thing together. We're going to, you know, it's going to take more than one solution to this. So you can go in and do other options, maybe treating the bosque. So what if we, you know, we went in and were able to thin out some of the bosque? How would that change things? So if this is all the public lands there along the river, so basically what we're talking about, if I can catch this guy, so basically getting rid of the invasive species, the salt cedar and whatnot, getting back to more of a normal cottonwood gallery along the river. What would that impact along with our trying to save some of the water through the low flow appliances? And you can see here we had little effect again on the depletion. This is because of the reduced or the use of the low flow appliances in our home. But now it did help us. It flipped us up above the compact balance now, so we're saving a little bit more water because we've gotten rid of some of these trees that use basically river water, the xerophytes, phreatophytes, I mean. So anyway, so you can see how you can use this kind of tool with a bunch of group of people. You can say, well, what if we do this or what if we do that? And build up different scenarios and look at different ways of meeting this balancing the water budget. So anyway, you get an idea of what one of these tools look like. We've developed these for many different cases. But now let me just kind of plow forward and talk about how from this little kernel of an idea it's evolved over time. And so starting with that idea and that model, which was an annual time step model, and it was just a lumped parameter model for one big region over the Albuquerque area. And so a lot of the water managers in the area, the Corps, the Bureau, and others saw this and they said, you know, we really like this idea and we could really see some cool applications for it, but it's just not quite technically detailed enough for us. Could we make it more detailed? And we thought, well, we don't know. Let's see how far we can take this. And so we started a project with them, and basically what they wanted was, they had all these tools, riverware models and mod flow models and all these different models for managing water resources in the basin, but they weren't put together. So it takes them a long time to look at different scenarios. So they wanted this rapid scenario screening tool. And they also wanted a way to be able to go out and educate and engage the public in various processes. And so ultimately they needed something that looked kind of like their ERGWAM model, the Upper Rio Grande Water Operations model that they're using, that represents it really well but runs really fast. And so basically, again, we developed this collaboration. Now the stakeholder engagement was largely with these folks, the technical folks, but to kind of create this scoping level tool that would become part of their toolbox of tools that they use to go out with the public. And so what we did here, instead of just having this one reach here in the Albuquerque region, now we've expanded it to 17 different reaches defined by the different gauges along the river, both the Rio Grande and the Chama. This is the Colorado border all the way down to Caballo Reservoir. So this is the basic Upper Rio Grande reach in terms of the compact. We also have 7 different reservoirs modeled and all their operations rules added to it. And then we've added 3 groundwater basins where there are mod flow models to build off of. And basically the way we did this is we patterned our model exactly after that, the tools that the Corps, Bureau, and others are using to manage the river, but at lower resolution so we can get this to run really quick and to get it all put together and operate in a dynamic mode. So we're using the basic physics that are in the riverware model. The only real difference is we're operating on a monthly basis instead of a daily basis like the Uruguay model. And we're also using the same evaporation package that they're using, again, based on monthly average data instead of daily data. And then we've taken these mod flow models, these monstrous models with all kinds of spatial detail, and we've simplified them down from hundreds of thousands of cells to about 50 here in the middle Rio Grande, kind of similar for the Socorro and the Espanola Basin. But the idea is we're giving up some of this spatial detail, but we still have enough variability to see where Albuquerque is and where the hot spots are. So again, the idea is we can use this tool to screen in on things, and then when we get there, we can then go and use these much more detailed models to hone in on the final solution. And so we've been using it in that mode in a lot of places. And again, it has a little bit of an interface, not as fancy as the other one that I just showed, but you can move these slider bars around and then get almost immediate results. Again, it operates very quickly, very much like the other model that I was showing you. And we can look at compact balances and see where variations in groundwater depletions occur within a basin. Here are the different reservoirs and their storage and how it may change between different scenarios. And here are environmental flows by different reaches, and so you can identify where different scenarios might be impacting those deliveries. And so we've used this tool. I guess I should step back real quick. That first tool that we used, it ended up becoming the basis for the that regional water plan. This model then has, like I say, has now become part of the package that the Corps, the Bureau, and others use to reach out to public in their interactions with the public, and also as a screening tool. And this was kind of an interesting study that we did where we were able to look over 1,000 years. They developed 1,000 different realizations based off of 400 years of tree ring data. And so what we did was we looked at all these different scenarios to give them an idea of which ones they should be looking at in their Uruguay model, because it takes them hours to run a model. It takes us seconds. And so we were able to screen over all these. And one of the interesting things is these are the storage in all the different reservoirs, average annual storage. And you can see the blue here is for that 1,000 runs of the 400-year data. And you can see, and then the red here is for, over the last 25 years or so what the storage has been. And you can see that uncharacteristically high, for the most part, storage has been in these reservoirs relative to what we would project to be in these reservoirs if we had been able to look over the past 400 years if we were able to run that. So again, some kinds of information that you can do with these kinds of tools that you couldn't possibly do with the Uruguay model and some of these higher fidelity tools. Another thing another step, the state engineers realized that in order to really be able to manage and deal with drought in New Mexico, we need some ways of being able to move water around rapidly from senior users to junior users. And one idea is through water leasing markets. And so what we've done is created this virtual market that allows us to do some experiments around it and see how these things change over time. And so this is a project I've been working with some folks at UNM on, as well as University of Chicago and a few other places. But basically we took that Uruguay model that we have, so it runs all the physical water availability and storage and other things, and we've put this market interface on it. And it allows like 15 people to get together in a room and play like people who might sell and trade, or I should say lease their water among each other. And so you can come in and put a bid to buy or sell water, and then the other guys playing the game would see it, and you play different types of people and at different reaches of the river, and basically you get paid for how well you play. And so it's a way of collecting information on how people would react to a market, and helps us to design a market without actually running it before you're ready to, right? And so with this kind of thing, you can see how water might move around in a market and whether there's problems with that. We're able to see what the financial gains for everybody in the game. Does everyone end up better off, or are people at a disadvantage? Also, we're able to compare it to some economic theory to see how the prices would change over time, and that they in fact behaved like we would expect. But more importantly than that, we were able to show that this seems to be an idea that would work pretty well. And so now, based on this, the state engineer has asked us, we've got some money through the Bureau of Rec to actually implement these ideas down on a small river segment in southern New Mexico to see if we can't get a real leasing market going down there and then use this to move it to other basins in New Mexico. Another thing that I've been recently working on is, so all of these other tools we've been talking about are, we've got these slider bars. We just assume that whatever it is we're interested in doing, we can do it. So I can reduce agricultural irrigation by 50%, or I'm going to go and line my ditches, or I'm going to have 50% of the people use low flow appliances. Well, that's not the way it works in the real world, right? You got to come up with a policy mechanism to try to cause people to change whatever it is they're doing. So we would like to bring in that human behavioral component into our tools. And so what we're starting to do is take these system dynamics models that we're using to do most of the modeling, so that provides the environment behind us, and link that with agent-based models, which gives us an ability to take a look at the human component and put that together. So we're linking the system dynamics, the environmental models, with agent or human behavioral models. And one of the other things that we're trying to do, again, back to this idea of kind of collaborative modeling, one of the hardest parts of these agent models is really developing good agent models. So the idea is, well, let's bring the people in and let them play. And by playing, they're going to expose some of their behaviors and some of their intentions and their values and whatnot, and using this information to try and create agent models and to learn from. And so we happened to connect, Intel's got a big plant there in Albuquerque, and I had some buddies from way back from Intel, and we got to talking about putting together a serious gaming interface. And they have this system called OpenSim, where it's an open software system that they're really trying to get people to use. So they decided, well, they would build a model for us that would sit, again, on top of our Erguam model. And the idea is it allows people to play out. And so you got your little avatar here, and they're able to walk around in this environment and see what's going on. And you can either be a farmer, a farmer, industrialist, or a home builder, a developer. And so you pick what kind of person you want to be, and then you go out, you buy pieces of land, and then you can decide how you want to develop that land each time step. And so if you're a farmer, you get to decide how much of the land you develop, how much you plant, and then you get to decide what kind of crops you want to grow. Each, has a different value and a different susceptibility to drought. And then otherwise you could be a builder and, build houses. And again, you have different options for houses and kinds and how many you build at a time. And you've got a certain amount of money you can work with, and then drought and economic downturn occur. And it forces people to trade and move water back and forth. And so, again, the idea is to have them play these games so we can get at some of the important things, both through the gameplay itself and also the debriefing after the process. And so this is something we're just really getting started on, but gives you an idea. Again, really kind of a whole new way of engaging people. The younger generation would get into this, but I mean, there's a lot of older players like us too. Just the hanging shovel here just means these houses haven't been built. But anyway, to give you an idea. So kind of another layer on this onion is another project. This is an NSF, Natural and Human Coupled Systems project that we're working with folks down in at New Mexico State. They're the lead on this. I'm supporting them through the integrated modeling. But this particular project, we're looking at acequias, and acequias are the irrigation systems that the Spanish came in and put in New Mexico back in when they first settled the land. And what's interesting about it is that these acequias are a lot more than just an irrigation system, an infrastructure. They're also a way of life. They're kind of the central aspect of the community. And the whole community revolves around these acequias and the schedule of the acequias. And it's also a way of managing water that's very different from our state constitution. And so what we wanted to do is to capture that system, this multidisciplinary system, and try to understand how it's affected by climate change and urban development, and basically why people are leaving and how we can help hold them to the land. And so we're looking at this at 3 different regions in the northern part of New Mexico, 3 different of these acequia systems and their associated uplands. And in this, we're trying to not only model the hydrology, but the upland and the riparian ecosystems and how they interact and the environmental services that the hydrology provides for this. And then how folks respond to drought and urbanization in terms of the economics. How are they able to stay on the land? They're not making a living. So how are they able to stay on the land? And then what are the social dynamics that hold them to that land even when the economics really aren't there? And so we're trying to pull this together to help ultimately make these systems, these communities, this rural to urban nexus, if you will, more resilient and help these communities remain. And I just put this in to say, you know, I've been talking a lot about the Rio Grande. I don't want to give the impression that's the only place that I or our team works. We've been working all over the world. We've actually done some work here in Barton Springs in Texas and along the U.S.-Mexico border with the Rio Grande, but we've worked in Libya and the Canada border. We've worked Iraq and Jordan and other places. And basically this Rio Grande has kind of helped provide an incubator or a test bed for putting a lot of these things together and then moving them out to other places around the world. And part of an effort to do this, I've been working real closely with folks from the Corps of Engineers, their Institute for Water Resources, and from the U.S. Institute for Environmental Conflict Resolution out of the University of Arizona, to create a community of these collaborative modeling folks. And so the idea is to bring them together, begin learning, and you know, feed off of each other. So we've had a series of conferences, 3 conferences, 1 every other year. We've published some books and proceedings, and some of the other things that we've done or developed some best practices, metrics of success, and then lists of surveys and other things. So again, things that people need to know, to kind of get in this and to use, you know, kind of build off of what we're learning, you know, as we go along. Kind of taking a little different step here now. So, you know, everything I've been talking about largely has been on that watershed scale, kind of more local type analysis, more local type watershed planning. But these ideas also have a broader footstep, and we can take, you know, a broader view. And this is a project that, and I think has some interest here in Texas, and it also is partly housed here in Texas, is that we're looking at this energy-water nexus in the Western and Texas Interconnect. So this is probably the first of its kind that I'm aware of where we're actually working with the large transmission entities out west, ERCOT, which is here in Texas, and WEC, which is out the whole western U.S. So they're looking out into the future and saying, how do we build out our future power plant fleet? And then we're bringing in the water managers from the Western States Water Council and the Western Governors Association to work with these guys to help with this planning process. Of course, this is all funded through DOE and we're working with various partners. I'm the lead here, Sandia, for this part of the project, the water project. And then we have 5 other national labs, the University of Texas and EPRI, supporting us on this project. And basically, again, the idea is to help kind of reduce that future water footprint, particularly stress over development of future water resources for thermoelectric power production. And so we're creating some tools to help them to visualize that and to work within some of their planning tools. We're engaging stakeholders across the board in this process, the water managers, the utility managers, and then ultimately to bring this into the transmission analysis. And so for those of you who don't know, WEC's out west here. It actually includes part of Canada and a little bit of Mexico, and then ERCOT is a majority of Texas. And so we're looking at about a 20-year planning horizon going forward. And again, we're looking at new power plant placement and the transmission that goes along with it. And this is, it's not just about water, but for the first time, water is being taken into consideration in this process. And so, you know, they're looking at minimizing cost and maximizing reliability of the system, but now they want to put a constraint over water because they know that's an important issue now. And in terms of what they can do is they're looking for, what kinds of fuel, what kind of power plants are going to build. Should they be nuclear or wind, or what should they be? How big should they be? What kind of cooling type should we associate with it? What about a dry cooling or a open loop cooling, which has huge differences in water use? Where do we put those plants? And then if we do need water, what kind of water source might we use? So we've got a variety of criteria, a variety of objectives, and at least WEC is developing an optimization tool to actually do this. So with those criteria, constraints, and objectives, and basically, they're looking at new transmission, new generation in an optimal sense in terms of least cost and other things. So with this kind of context, it kind of constrains us on what kind of information we need to provide back to them. And ultimately, they need to know what that delta in cost for water will be and how that compares to other costs in their model. And then ultimately a constraint in terms of availability. And ultimately what they would like is a constraint in terms of megawatt hours. How many megawatt hours could I build here and have enough water to meet that plant's needs? And so we've been working with NREL, and they've been providing us information in terms of water use for different types of cooling for different kinds of power plants. And you can see it's all over the place. Different kinds of plants, different cooling. You get very different water demands. This is in terms of consumption. Water use is very different from there. But using this kind of information, and it's not only the type of power plant, but also as you look across the U.S., depending on what basin you're in, depending on the temperature, latitude, altitude, and other things, that water demand is going to vary a bit. And so we're creating these maps of really for different kinds of units. So for like a coal plant using a certain type of cooling, we would get a map of water demand for, per megawatt hour. And so with that, then we can map our gallons of water availability to megawatt hours constraint in their model, okay? And so the other thing you're probably saying is, well, there's not just a cost for water, right? But different water are going to have different availabilities, and different sources of water are going to have different costs. And so we're going to try to create multiple maps looking at different water supplies or water sources. So in terms of potable water, we're thinking unappropriated water, where I can just go out and get, and I think there are a few places still in the West where you can actually go out and get a water right and use that water. Then there's appropriated surface water. That would be where I have to go buy a water right from a farmer or industry, mining somewhere, or groundwater. And then for non-potable sources, looking at municipal, industrial wastewater, shallow brackish water, and seawater. And so for each of these sources, we want to come up with two maps. One is at some rough measure of how much water is available in that basin, and then what would be the relative cost to utilize that water and to access it. And so what we're doing is we're working with all the states, and we're working directly with the state water managers so they have some confidence in the data we're using, but we're collecting all kinds of data. And so demand data in terms of different sectors, different sources. This is all by 8-digit watersheds, so you can get an idea of the resolution here that we've done for Arizona, consumptive use versus withdrawals. Also on the supply side, many different metrics in terms of gauge stream flow, groundwater, interbasin transfers, reservoir storage, brackish water, all these kinds of different potential sources or supplies of water. And then these institutional factors. Just because there's water there doesn't mean I can access it. So things like compacts, what the state says is unappropriated water, Indian water, administrative control areas, adjudication status, so other kinds of information. So now we've got all these multiple layers of information, none of which tell me what I really want to know, which is water availability, right? And so the next step of this is, now that we have this data, we develop it in an interactive environment, kind of like I showed you a minute ago, so we can view it in a GIS format and then combine this information. We want to come up with metrics. So we combine this information in a consistent way to give us a consistent view across the whole western U.S., to give us a relative measure of water availability for every Huck 8 basin in the West. And so this is one we're working on right now for brackish groundwater, and again, we're working directly with the state water managers. We have a handful of them, 5 or 6 of them, that are working with us on this process. And so for this case, for Texas and Arizona, we have these measures. And so we can just take that measure out. But for a lot of the other areas, we have no idea. So we're using other indicators for water availability, brackish water availability in terms of water use, brackish water wells. And again, we're just beginning to really get working on this, but the idea is eventually we're going to come up with this relative supply metric for brackish water. Same thing, the cost. So based on the depth and salinity of the water, we can come up with a rough cost of what it would take to access and use that water. And so this would be for the brackish water, but we'd have 4 other indicators that all go together, and then we can slip them in that model for the optimization, and it constrains where they might locate future power plants. The last thing I'll talk about is something and again, so here we're looking at the West, now we're looking at the U.S. and beyond, and adding really another layer of complication, that's climate change. And so I'm working with several folks at Sandia, in which we're looking at integrated assessment modeling. And so the idea here is that and what's kind of unique is we're looking at it more, not just using the mean deltas in climate, where temperature or precipitation or whatever, but looking at it more in a stochastic sense, looking at that full ensemble of uncertainty, running it through some simple water resource models, and then into an economic model, a RIMI model, to look at the economic impact and to look at how that varies across the U.S. Who are the gains and the losses potentially on this stochastic idea. And now we've done this, we have a report out, we're going the next step and now trying to extend this more on a global state by nation. The final thing I'll mention is I've also been working on the National Climate Assessment, so you might the U.S. has to put these out every 5 years or so. The last one was in 2009. We've got one coming out in 2013. We're doing these integration reports or technical reports right now. And I was one of the lead authors on the cross-sectoral chapter for energy, water, land. This is the first time they've looked at this chapter. So it gives us an idea of where kind of the body of literature and research is going and what are some of the issues and opportunities there. I also did the energy piece for the Southwest regional climate part. So getting involved with that environment, and I mean this is just kind of the next step we've got to add into all these models, whether it's climate change or climate variability, however you want to look at it, something that good planning is going to have to address. So just some parting thoughts. I think this is an exciting time to me. I mean, this idea of sustainable development, sustainable resource development, I think is probably one of the most important problems facing our generation, and I'm excited about being part of that. I know all of y'all are. I mean, that's why you're here. And I think that's really exciting. And, I think this collaborative modeling, it's not the only answer, it's not the only solution, but I think it's a valuable tool that we need to really, and many people are doing this idea, we got to keep working on it, and that's integrating, the stakeholders directly within this modeling and using them and using their knowledge to come up with good solutions. So with that, I will quit talking, and I don't know if you want to do some questions or how you want to handle it from here. But thank you.
So round no more than 8 questions per person.
Vince, what have been your role or roles in the model? Somebody coming from hydrology, was it more technical? Was it the social design, the software structure?
Well, usually in most of these projects I will lead the modeling, so kind of helping to frame it and being very responsible for working with the public and integrating that information. I generally do the hydrology modeling because that's kind of where my background is, but then I generally depend on other disciplinary experts to put the other pieces together or work with me or one of my staff to put those pieces together and integrate them into the tool. It's,
Just to follow on Ari's question, for example, you mentioned Riverware, a software system I'm sort of familiar with, and I was at a conference and the director of Tidwell was there.
Yep.
I asked her a question,
Edie.
and I'm about to ask you a similar question. I asked her, how much did it cost to develop Riverware? And she told me $15 million. And I thought, my goodness, here's a computer program, these computer programs. How do you spend $15 million to develop a computer program? I'm going to ask you a similar question. Can you comment upon just the effort, the number of people?
Sure. And so we've taken a different approach in that I'm not as interested or as capable to develop a kind of a set piece of software like Riverware or whatever. We've gone at it more that we build from the ground up because we're meeting with people all the time and everything's a little different. We create modules, that we can reuse, but so ours is from the ground up. And I mean, so what does it cost? And I mean, remember, DOE dollars are not real. I mean, but even so, we can, depending on how much from the ground up we have to work on these and, who's gathering data and all that kind of thing, these can run anywhere from, I've done some work for as little as $25K where I've had some tools that didn't require a whole huge amount of change to we probably put over $1 million in this Rio Grande model just over the years because of the longevity and all the different people we've worked on and all the different things that we've added to it. So it's all over the place.
So that has to translate to a large number of scientists and participants.
Yes.
In the effort.
Yeah. Well, and I mean you have multiple classes in the sense that you have the folks who work directly either to gather the data, then those who are building the models, and then usually you have the team of stakeholders who really aren't building the models, but they're meeting with you on a fairly consistent basis. So, yeah, the community gets pretty big.
So, Vince, so besides the systems part, what are the science challenges that you encounter in this kind of modeling? Maybe in your scenario analysis or uncertainty analysis, you might be seeing that. So if you say everything is accurate in the models, then only everything works here. But if you come back in the reverse directions, what is your science challenge to deal with?
Well, I mean, they're the same challenges all of us face, right? I mean, there's not enough data, there's uncertainty, there's, and then you're always kind of faced, I do a little teaching and, I always try to stress the students, modeling is as much an art as it is, a real hard science because, you've got resources, you've got a question to answer and how do I, best answer that question with the resources and data and whatnot that I have to do it with. So I would say all those things are, just the same as any modeler faces. I think what makes this maybe a little harder, but it's also a solution in a sense, is that now as you start reaching across multiple systems, those issues just compound. Part of what we do usually in the systems level is, I've backed off a level, so I'm aggregating at we always are aggregating in some sense, but maybe more so than a lot of the more detailed mod flows or riverwares or whatever. So that can be a benefit. It also can be a problem. The other issue is that, when you start opening it up to the stakeholders and their engagement, they understand more what's under the hood and they become more demanding. And they can at times become a little disillusioned in that, someone pulls out some nice model that they had no involvement in. It all looks clean and beautiful and, so you're exposing yourself to greater scrutiny. I think part of the other thing, though, that we try to do with this, and again, with these system level models, we are able to do stochastic analysis if we need to, because we can afford to run lots of simulations. The other nice thing is that it's fairly easy and fairly intuitive in terms of the way you construct these things. That if you have competing theory or competing different, do I add this extra physics in there, or can I ignore it, or do I have to put it, disaggregated at this level or whatever? A lot of times you can go in and you can play with some of that at some level and see how hard, what impact it has on your model or your results or your questions, and sometimes you can just resolve it that way. Yes, sir.
How do you go about dealing with the connection between the modules? How formal is middleware? And is it the process of formal linkages or intuition?
Well, it depends a little bit on a lot of what I was showing are all built within a system dynamics framework. I don't know if you're familiar with system dynamics like Stella or PowerSim. We use PowerSim a lot. Those, it's a very tight coupling. It's all built within the same framework, and the trade-offs are all, the couplings are very tight. There are other cases where we'll go outside and build separate models, and again, it just depends on what we can get away with in terms of how tight we couple it. But that's where the real interest is, and is across those interfaces.
I'm interested in how you put together this team to look at social and using the models to help evaluate the social implications of water use and those kinds of things. I mean, did you have a behavioral scientist working with you in terms of developing the tool and everything? And then how did you develop your assessment relative to their behavior using the tools?
I think the best example is the Acequia, this coupled human natural system project through NSF that we're doing. And it's a real challenge, and we're still in the midst of it. We do have some social scientists. There's a couple of folks in particular that are like the world experts on acequias in these rural Hispanic or Spanish cultural and irrigation systems, and they're very qualitative. I mean, they do very great work, but it's all largely qualitative. And so in terms of figuring out how do you take, and they do surveys, but again, it's usually not to get to a really hard quantitative number. And so what we've been doing so far, and I think we're making progress, but we've yet to really put numbers to a lot of it. We're setting up surveys right now to try and help move this to more quantitative stance. But the figure I was showing that has these causal loop diagrams, these causal models, is we've been able to mine a whole lot of information out of the folks by going through this and working with them to understand what's the causality within this social network, and how does, what is it that, moves us to making, helping a community member decide to move off his land. I mean, ultimately, it's not an economic decision in most cases. So what is it that's holding him to the land? And then what are the processes out here that, feed into that? And then how are they, in turn, affected by climate or the ecosystem that they're living within, or the job market here in Albuquerque, or whatever it is? And so the first step in that's doing that mapping, that causality. It's just what we all do as modelers, right? And then we're doing a series of surveys, learning from that, trying to construct some surveys that'll give us some quantitative data that are a little different from what they're used to doing, and then pulling it together in a model, and then working with that community, So this is what we think you do. What does it look like? Do you agree? And
I think that you could reduce the number of people that you would be interacting with in order to get the same quality of information, because surveys go out to a large number of people. It's how do you pick the population of people that you're actually trying to gather information from, And
well, usually what we start with is a mapping of all the key stakeholders, right? And then you try to decide who are the key ones, and you make sure you get those covered, and then you get as much of the others as you can. I mean, I don't know that that's rocket science, but I mean, that's pretty much the approach we've been taking. And getting surveys done and back, are always a challenge. I find the more dire, if you will, the situation is, the more cooperation you get, right? And that's just the way it is with planning. If people are more concerned about the future than they are of the uncertainty about what if I try to do something or do something different, then you get some movement. Otherwise, nothing ever happens.
We've got time for one more question.
What about the quality side of the coin?
Oh.
Integrated into this, things like non-point source, bacteria, nutrients, there are a number of us work in that arena.
Absolutely, and absolutely you can do it. We're just happy to have water in the river, and for the most case in New Mexico, but we've done some quality modeling. In fact, one of my colleagues that I work closely with, we did a model up in the Willamette, and there we were looking at temperature modeling, and we had the different reservoirs and how they turn over and their release schedule and how that affects the water temperature, and then relating I think it was a 5-day maximum temperature, which was their biological opinion constraint on the river, and then seeing how that would change with building or planting trees or shading and a lot of other things. And so that's probably the biggest we've done. I've also done some nutrient and salinity models that I didn't show here. We've actually, working with folks from the U of A, had some students build those components into the model. So yeah, I mean, it's very much doable. It's just seems like most of the problems in New Mexico, we hit the water first, because that's the big issue. Not to say quality is not important, but.
Before we wrap up, I just want to remind everybody that at 1:30, you're invited back for continued discussions with Dr. Tidwell. I think we'll have other faculty members join us at that point from AgriLife Research, AgriLife Extension, from TEAS, from engineering and TEAS, so, and geosciences, I'm sure. So if you will, just join me in thanking